Anyway, what I want to talk about today is power series. Power series I really like. I think it's a very interesting and really kind of super interesting discovery that was made about just the existence of power series, and extremely important in terms of the development of math and science in like the 1800s. Like power series really enabled people to do lots of stuff that they didn't know how to do before. And I think it's a super interesting and like very weird and extremely abstract, but at the same time very down-to-earth kind of a thing and super useful. So anyway, a power series is, maybe you've heard of this before, basically it's like an infinite polynomial I'll put that in quotes because we don't call it a polynomial anymore because of the infiniteness of it, but it's something that looks like, and you think of this as a function where I'm just writing coefficients. Polynomials, of course, usually when I write a polynomial, I like to start on the highest degree and sort of go down to the constant at the end, but actually when you're writing an infinite one, sorry, that should be x squared and then c3 x cubed, ... So this just goes on forever. It has coefficients just like a normal polynomial does, only there's infinitely many of them, and it has powers of x, but there are infinitely many of the powers of x. So it doesn't have a degree in the sense that a polynomial has, because it goes on forever. But this you can still think of like a function. We write this, of course, as a series, c n x to the n, right? And so it is just a normal series, only it's a series where it's also a function. So we can think of it like a series, which it is, but we can also plug in values of x and get answers, right? And so this is sort of, when this kind of a thing was discovered, this was kind of viewed as like a new kind of function. It's not a polynomial because it has infinitely many terms in it, but it is still a way of defining a function where you can plug in a value of x and then add up the series and you'll get some kind of answer. Or maybe the answer will be it diverges for this value of x and it converges for some other values of x. But we can plug in values of x and get answers. And so this series, a power series like this defines a function f of x, right? And it's a natural question to ask yourself, what kinds of functions can I make by creating functions in this weird way, right? This is an interesting question. Like you could also ask, for instance, all your like favorite functions, sine and cosine. Is it possible to express them as a infinite polynomial like this? Like everybody knows, sine and cosine are not equal to some polynomial because they're just not. They are different kinds of functions. They are not polynomials. But maybe they could be equal to a power series like this. Is every possible function you can ever think of the same as a power series like this? Or are there some functions which cannot ever be expressed as a power series? These are the basic questions that everybody became interested in as soon as this was kind of invented, or as soon as people started thinking about this. Anyway, let's talk about the simplest possible example of this is when all the coefficients are 1, right? That's the easiest way, version of this. So one example, I suppose really the simplest possible would be if all the coefficients were 0. But let's consider all coefficients equaling 1. That would look like this. Of course, we would write it like this, the sum of 1 times x to the n, where n equals 1 to infinity. The natural thing we always ask is, does this converge or not? But for a power series, you don't really ask, does that converge? Because this, as is, this is not a number. It's just a bunch of x's. The real question is if I plug in certain values for x, will it converge? And if I plug in certain other values for x, will it diverge? Really, the question is I will say, at least for today, what we're going to be talking about, the usual question is, for which x does this converge? Right? And usually the answer is like, well, it converges for certain x's and it diverges for other ones. Like this one, for instance, certainly it does converge if x equals 0, because then it's just 1 plus 0 forever. And the answer would be, sorry, if I want to write this technically, I shouldn't have a 1 there, right? Because the n starts at 1, I never get the 1 at the beginning. Or you could change it to x to the n minus 1 power. But anyway, if I plug in 0 here, it does converge. If I plug in 1 here, it diverges, because if you plug 1 for x, this just looks like 1 plus 1 plus 1 plus 1 forever, and that diverges. So there are certain values of x for which it converges, and certain values of x for which it diverges. All right? How could we tell in this example? Actually, in this example, this is very easy. This one is a geometric series. Remember, geometric, those things look like, something like sum of 1/2 to the n or something. That's a geometric series where the r, what determines if it converges or not is the r, that is that ratio of one term to the next. This one is geometric with r equals, can anybody say what the r is? Remember, that's the ratio of the next term divided by the previous one. It's just x. Yeah, if you look at these terms here, to find the r, you would go the second one divided by the first one, x squared divided by x, which is x. All right, so the r is x. And so for which x does it converge? Remember, the geometric series, the rule is it converges when absolute value r is less than 1. And it diverges when absolute value r is greater than 1. So this one is geometric with r equals x. So it converges when absolute value r less than 1, which means absolute value x less than 1. And it diverges when absolute value x greater than 1. Can you read what I said? They got it. All right, so this one converges when x is less than 1, and it converges when and it diverges when x is greater than 1. And in fact, we can also say what it converges to. So when absolute value x less than 1, it converges to, remember what it converges to is a over 1 minus r, right? So this would be x over 1 minus x. All right? And this is actually a strange but true fact. So this is a true fact for absolute value x less than 1. The series x plus x squared plus x cubed plus blah, blah, blah. This actually adds up to x over 1 minus x. It's true. This is a true fact. Only when x is in absolute value, when x is less than 1. If absolute value x is 1 or more, then the left side is infinite, but the right side is whatever it is. All right? This fact you will also see written, if you can just divide both sides by x. Everything on the left side has an x in it, which you can take out. This is also written sometimes like this. Like that. This is the more common form for this strange but true formula. All right? So what you can see is this function, this is a fairly ordinary looking function, which is not a polynomial, but it actually equals this infinite polynomial, where this is equal, not always, this is only when absolute value x less than 1, right? Otherwise, the left side is infinite, but the right side is not infinite, so they're not equal anymore. All right. All right, great. So the big question is, I give you a power series, and I ask you for which x does it converge, and furthermore, if you can say, what does it actually converge to? This is the typical question. And maybe we'll do, I got 2 examples, and then I have one for you all to try. And this is what sort of the homework questions you can expect. For which x does it converge? And in order to do this, we're going to use the various convergence tests. So you can use the comparison test, you can use the integral test, you can use the ratio and root test. It turns out actually for these examples we are usually going to use the ratio test. It turns out that's typically going to be a good way to do these. Anyway, let's try this strange series here. This one happens to start with n equals 0. It really doesn't matter. I mean, the techniques are the same anyway. This is a very weird, although this function kind of comes up every so often in applied problems. This is called the Bessel function of order 0. I actually know essentially nothing about Bessel functions, but next time you're in the club or something, you can just name drop the Bessel functions. They'll be like, oh yeah, the Bessel function. Some people are really into this. They come up in various applied settings, although in my mathematical career, I don't do a lot with real world applications, so I don't do much with the Bessel functions. But anyway, for which x does it converge is the question. And you can use any of your various convergence tests. Now, the previous example we just did, it straight up was a geometric series, and this is not, so we can't just do it by finding the r like we did there. But how about, let's use the ratio test. It turns out the ratio test really works quite well for most of the examples we're going to do. So this should be like your first attempt. If for some reason it doesn't work, you can try the integral test. Although I actually don't recommend the integral test. Anyway, let's just do the ratio test. So I hope everybody remembers the ratio test is this one. And you want to show, anyone remember how the ratio test goes? This is on the homework that's due tomorrow. This we called L, and then it said something about if L whatever, then it converges. Anyone remember this? Yeah?
Is it greater than 1 or less?
Well, yeah. If L is greater than 1, then it con or die. If L is bigger than 1, then it diverges. If L is less than 1, then it converges. What I think of this is basically this is kind of like the R from a geometric series. Only I'm in a geometric series, these ratios are always equal to R. In an ordinary series, it's not a geometric series. These ratios may be different from one another. But anyway, the same condition as the R over here. If that ratio is more than 1, then it diverges. If it's less than 1, it converges. And if it equals 1, then you don't know. So actually, well, you'll see it's not going to equal 1. Lucky for us. Anyway, let's do it. So here I go L equals lim n goes to infinity. You need these absolute values, but then I'm going to plug in an plus 1 divided by an, and I'm going to write it as multiplying the reciprocal. So this is minus 1 to the n plus 1, x to the 2n plus 1 over 2 to the 2n plus 1. This is a little complicated. N plus 1 factorial squared. All right, that's an plus 1. We just plugged in what you see at the top, but I plugged n plus 1 instead of n. Can you see what I'm writing?
Not really.
You want me to big it up? Is it just messy? It's like that, right? I'm plugging in n plus 1 instead of n. And then I go times the reciprocal of an, which would be just the original formula. I scrolled it out because I'm trying to see the original formula there at the same time. The original formula, but in the reciprocal. So it's 2 to the 2n times n factorial squared over minus 1 to the n x to the 2n. And all of this is inside of absolute value signs. All right. This is quite complicated, but hopefully we will cancel out a lot of stuff here. So what can we cancel? I got minus 1 to the n plus 1 and minus 1 to the n here. Those are actually, since everything is inside of absolute value signs anyway, these minus 1s can just disappear, right? These are going to affect it by changing the signs, but it doesn't matter because they're all inside of absolute value. So can I just straight up X them out? They're going to get absolute valued and they will go away. We also have powers of X. So maybe I'm going to rewrite this, but distributing some n's or 2's, and I will group together the like terms. So let's write the powers of X. I have x to the 2n plus 2 on the top and x to the 2n on the bottom, all right? Then I have powers of 2. I have 2 to the 2n up top and 2 to the 2n plus 2 on the bottom. And then we also have the factorial parts, n factorial squared and n plus 1 factorial squared. Right? I hope I didn't screw it up, but I think I'm just gathering together. And now we can do some serious canceling. What do you get from the first fraction there when you cancel? Just this guy here? Yeah?
X squared.
X squared, yeah, right. X to the 2n plus 2. Remember, in a situation like this, you should be subtracting the exponents. And so it's 2n plus 2 minus 2n, which is 2 in the exponent. X squared, all right? Don't forget about these absolute values. Actually, you will see in these kinds of problems, you know, usually when dealing with absolute values in calculus, there's some step where I say, okay, now the absolute values don't matter anymore. But in these problems, actually, the absolute values will survive all the way till the end, unfortunately. This can be a little confusing to deal with at times. Anyway, the next one, what's left over from that fraction? Somebody else? Canceling master? 1/4, yeah, 1 over 2 squared. The same idea about subtracting the exponents. 1 over, I'm going to write it like that, just so it's maybe a little clearer. And the last one, the factorials. I don't know if anyone is hip to factorial business like this. Maybe as a step towards simplifying, you can write it this way. That whole thing squared. Anybody know some rules about factorials? Here's one terrible idea. Can I just like cancel the hays? That's the factorial sign. The answer is no, you can't. That is an operation. Unless somebody told you once that was allowed, you should not feel like that's allowed. It's not allowed. Anyone have a better idea than that? How about n plus 1 factorial? Is that the same as n factorial plus 1 factorial? Anyone got thoughts about that? This also is not true. That would be like, I mean, you can just work out examples and convince yourself that it's not true. Like n plus 1 factorial is a lot bigger than n factorial. How much bigger? Well, it's not just one bigger. It's a lot bigger, right? But if you believe that equals that, then you're saying this is just 1 bigger than n factorial, which is not the case. So you can't do that either. There were some factorials on the homework due tomorrow. Anybody get this far? Anyone have an idea what you can do with that? You can actually do something with that. Yeah?
Just n plus 1. Like, you cancel out like n factorial.
Is it just n plus 1? Something like that. Yeah, this right here, you want to think of this. Of course, n factorial means 1 times 2 times 3 times up to n, right? And on the bottom, n plus 1 factorial means you do all that stuff, but also go up to n plus 1. So it looks like 1 times 2 times 3 times, etc., up to n, and then finally to n plus 1, right? That's n plus 1 factorial. And so here, almost everything cancels. All that is left over is n plus 1 in the bottom. These guys cancel like so. And we end up with just n plus 1 at the bottom. So to summarize here, it says lim x squared times, I'll write 1/4 now, and then finally this thing becomes 1 over n plus 1 squared. All right. It's a little taxing the simplifying and whatever. Anyway, what can we do now? I think we can finally actually do the limit here. When I take the limit as n goes to infinity, what do you get from this? As far as this limit is concerned, this and this are constants because they don't have any n's in them. So really all you look at is here when I do this limit. What is that? What happens there? It becomes 0, yeah. So this entire limit is straight up 0. This usually doesn't happen, by the way, but this is, maybe you could say an easy example, I don't know. You get 0 in any case, all right? And so what does that mean? It means that the series converges, right? This L is less than 1, so the series converges. Actually, no matter what x is, that limit is always going to be 0, right? So the series converges for every x. It's because the x ended up not mattering at all in the limit. No matter what the x is, I got 0, and so the series converges for every x. All right? So that original thing that we started with up here, it may be surprising, I don't know. You can plug actually any value of x into this and it will converge, even though this is a kind of a crazy formula here. It will actually converge and it's never infinite. All right? Great. I got another one, and then I have one for you all to try, like I said. Let's try. This one's a little less crazy with the simplifying, but it's a little more interesting at the end, maybe. X to the n over 3n. The question again, for which x does it converge? This one, it's not going to give me 0 at the end, so it'll be a little more interesting at the end for this one here. All right, we're going to do the ratio test again. The ratio test should be like your go-to for all of these. I want to do ratio test. So it's this L thing. And it's going to be absolute value an plus 1 over an. That is absolute value. Okay, an plus 1 would be x to the n plus 1 over 3 n plus 1. That's an plus 1. You plug in n plus 1 instead of n. And then divide by, or I'm going to say times the reciprocal, 3n over x to the n, like so. All right. It looks kind of like before, a little saner maybe. Now we cancel as much as we can, simplify in here. I would say I have some powers of x and also some other, 3 times whatever. What happens with the powers of x when you cancel? 1? X to the power 1, you mean?
Yeah.
Yes, 1x. Yeah, x. X, right? I had x to the n plus 1. Canceling out x to the n gives me x to the 1. And then the 3n over 3n plus 1. I don't know, I guess you could cancel the 3's there, right? And otherwise, I'm left with x times n over n plus 1, right? And you absolutely should not cancel the n's right there. This is a rookie mistake, because that's not how fractions work. All right, anyway, can we take the limit as n goes to infinity? When you do this limit, you treat x like a constant in the limit. Treat x as a constant when we do the lim, right? The limit concerns only n, not x. All right. What does that other thing equal when you do the limit? You show me the fingers, if appropriate. I see a few people showing me the one finger, the good one, not the bad one. The limit of that part is 1. It's because this is a ratio of polynomials where the coefficients are just 1. So this gives me, so what's my final answer for this limit? X, also known as absolute value x. And the absolute values really are important here. There is no step where I'm just going to stop caring about the absolute values. You really need to carry them all the way to the end, all right? So, to summarize here, so L is absolute value x, so it converges when absolute value x less than 1. I should write this up here. It converges when absolute value x less than 1, diverges when absolute value x greater than 1. All right. This is not the full answer. This actually is, so we're almost giving the entire answer. There are some cases that are left out here. So it converges when absolute value x less than 1, diverges when absolute value x greater than 1. What about absolute value x equals 1? So what about absolute value x equals 1? We need to consider this as a special case. So this is an extra bit of stuff that you have to do at the end, typically in one of these problems. We need to consider special cases. There's 2 of them, right? What about absolute value equals 1? Sorry, I forgot to write the 1 in there. We need to consider special cases for x equal 1 or x equal minus 1, right? If the absolute value x is 1, that means that either x is positive 1 or negative 1. So these are the 2 special cases that we need to consider specially. So let's consider x equals 1. What does the series look like then? Remember the series was x to the n over 3n. If I use x equals 1, this becomes the series 1 over 3n. I'm plugging in x equals 1, right? And can anybody say, does that converge or not? Like in theory, at this point, you might have to use another comparison test or the integral test or something like that. Although hopefully they'll be simple enough in these special cases that you can just tell by looking. Can anybody tell by looking? Yeah? Why do you say it diverges? Yeah, because this is like a p series. Like that 3 in the bottom, you could, if you like, factor it out. And then this right here is the harmonic series, or you could say the p series with p equals 1, which diverges. All right, so for x equal 1, it diverges. What about x equal minus 1? Again, we got to consider that as a special case. So this time, using x equal minus 1 turns this into minus 1 to the n over 3n. And what is that? Well, this we can factor the 3 out. Again, minus 1 to the n over n, right? This is like a harmonic series, but it's alternating the sign. Does anyone remember this? Does that converge or diverge? This we also talked about. This is called the alternating harmonic series. And this one converges. It converges to like the natural log of 2. It has some weird value. But anyway, this one converges. That one diverges because this is the harmonic series, and you should just remember the harmonic series diverges. And this one converges because it is the alternating harmonic series, and you should remember that that one converges. It converges to the natural log of 2, but I don't care if you remember that. Just the fact that it converges or diverges. All right? And so, now we've considered all possible cases. You should say specifically what the convergence is, all right? To summarize here, it converges here, it diverges here, and it diverges here and converges here. Can we put all of this together? It converges when absolute value of x is less than 1, and it also converges when x equals -1. What that means is it converges when x is in this domain, right? We said it converges when x, absolute value x is less than 1, which means between -1 and 1, but it also converges when it equals -1, but it does not converge when it equals 1. All right, this is all summarizing the stuff that I had just said, and then diverges otherwise. All right, there's kind of a lot of details to work through at the end. The basic idea is the ratio test, and then there's some other random stuff at the end. All right, I got one for you all to try. It should go similarly. Let's check it out. How about, this is very similar, but I put the n as an exponent. X to the n over 3 to the n. All right. Again, I would suggest you use the ratio test. Although this one, maybe you could have used the root test also. Although I prefer the ratio just because it's my go-to. It's my main. By all means, chat with your friends. Oh, I got some random old papers. Here we go. So far, yeah. Cancel. It's that cancel culture. Yeah. Great. We should still have absolute values there.
What do I do if there's no more n and no value? I should optimize.
Then that is the.
Oh, right, because it's constant. Okay, thank you.
All right. Should do the ratio test, which means an plus 1 divided by an.
Oh, it's 1. It's not x.
So one of these stars so I think how do you say
It's the same thing, it's just x. That's what I'm saying. But it's the opposite.
and then you also have
It's minus n. Right, okay.
Alright. It should be the sum. And so this means 1 plus 1.
It should be x over 3.
How's it going?
This 3 is negative. So it's x times 1. Oh.
So all your How's it going? All right. Okay. Yeah. And then you check each.
Yeah, check.
All right. Yes. Yeah, so then when you do the limb, there's no n in there.
-3 and 3.
The one just equals that. Yeah, that's great. And then you say, so the convergence when this is. Uh-huh. Yeah, so here, to do the limit, you just go with that, right? And then you say convergence to that is less than 2. Alright? So there's no n in there. There's no limit of this. It just equals that. And that's the L. And then you say convergence to that.
It's not going bad.
I think it should be the 3. Uncancel 3 from the bottom.
So it's actually worth it.
Yeah.
But no, that's just your real.
So that's the L.
And then you plug in 1 and -1.
Not quite really. So you say converges when it is less. How's it going?
Sorry, my snap's not.
We plug it in x equals 3, so we'll say 3.
Oh, okay.
Oh, you want to talk about these? I see some people doing great. It's fairly straightforward, although there's some sort of ins and outs you got to deal with. So when I do the ratio test, as usual, it's going to look like L is this lim an plus 1 over an, which is lim x to the n plus 1 over 3 to the n plus 1, and then times the reciprocal of an, which is 3 to the n over x to the n. We cancel, and we get lim n goes to infinity, absolute value x over 3. And then this limit, there is no n inside here, and so the limit is just equal to this. This is as if you're taking the limit of a constant, which just equals that constant if you don't see n in there. So this L is absolute value x over 3. All right? I think pretty much everybody got this far. And then you say, so it converges if the L is less than 1, which is to say, i.e., absolute value x over 3 less than 1, which I find it better to multiply both sides by 3, and it says absolute value x less than 3. So this is where it converges. And it diverges when absolute value x is greater than 3. Diverges if absolute value x greater than 3. All right. Now you could just leave it like this, although to me this is a little more cryptic. I mean, this I can tell what this means. It means x is between -3 and +3, right? Whereas that is a little harder to understand. All right. And so it converges if x is an absolute value. This is converge. And it diverges if the absolute value x is greater than 3. As a special case, we need to check what if absolute value of x equals 3. So this is the very last kind of technicalities at the end. So we check if absolute value of x equals 3. That is to say, x is plus or minus 3. So there are two special cases. One is plus 3 and the other is minus 3. So I check x equals 3. All right, my original series was x to the n over 3 to the n. I plug in 3 for x. I get 3 to the n over 3 to the n. And then try to simplify this and figure out if it converges or not. How do we simplify? Well, it's just you cancel entirely, right? This becomes sum of 1. And then does that converge or diverge? This means 1 plus 1 plus 1 plus 1. What do you say? Converges or diverges? it diverges when you go 1 plus 1 plus 1 forever. It does not add up to something in particular, it diverges. All right, so that's my first of the extra cases. And then the other, x equals minus 3. We've got to work that out. And usually, these special ones are fairly straightforward, but you have to work them out. So it'll say minus 3 to the n over 3 to the n. Simplify that. This actually, you can kind of cancel inside the nth powers, and it will say minus 1 to the n. And what is about that? Does that converge or diverge? This is like minus 1 plus 1, minus 1 plus 1. We also discussed this. It diverges, yeah. This one also diverges. So all of our special cases diverge in this example. There is no real rule for this. You really just have to check them individually and see what happens. So what's my final answer to summarize everything? It converges here, and it diverges in all of these other situations. So here, meaning absolute value x less than 3, I like to write that as a little sort of triple inequality. It converges when absolute value x is less than 3, which is to say minus 3 less than x less than 3, and it diverges otherwise. Diverges. There you go. This is how we do it. One thing that you may notice, all the examples we've done so far, the answer in terms of where it converges has always been an interval. This is an open interval. The previous example was open and closed on one side, but this is actually a theorem. I'll say it in detail next time. You always get an interval for these things. One interval. All right, I think that'll do it for today.